So today we are reviewing for exam 2 here in Calc 2. And we have done a lot of topics since early March. Since the last exam, the first topic we did was polar coordinates and calculus with polar coordinates. And then we did lots of applications of integrals. And then we did lots with sequences and series and Taylor series. What you could say this content has been the heart of the course, the heart of Calculus 2, though I would probably also include the volume problems in that as well. We did that for exam 1. With polar coordinates, you should be able to do basic things. Basic things would include converting between polar coordinates and rectangular coordinates. So let's just draw a basic picture here to start with. You got an XY plane, and you've got a point in that plane, a point P. That point can be described either with rectangular coordinates or polar coordinates. The rectangular coordinates are based on the spot on the x-axis that it's above and the spot on the y-axis that it is to the right of in this case. I could call those x and y as well, so I'm using the letters x and y, both for axes labels and for these numbers on the axes. If you draw a right triangle in here, the distance along the hypotenuse of that triangle, that right triangle, is the polar coordinate r, and the angle that the line segment there makes with the positive x-axis is the polar coordinate theta. To convert from polar to rectangular is the easier one. You can just use these equations directly. X is r cos theta, y is r sine theta. You should understand where those come from. It's really trigonometry, right triangle trigonometry, in fact. So katawa, right? So sine is opposite over a hypotenuse. Sine of theta, right there, is the opposite side, which is x, divided by the hypotenuse, which is r. Multiply both sides of that equation by r, and you get that equation. Cosine, cosine is adjacent over hypotenuse. Oops, I guess I just did that. Okay. I did the wrong one. Let me say that again. So sine is opposite over hypotenuse. The opposite side for that angle is y. The hypotenuse is r. Therefore, you multiply both sides by r and get y equals r sine theta. Cosine is adjacent over hypotenuse. The adjacent side is x. Cos theta is x over r. Multiply both sides by r and get this equation. To convert backwards from rectangular to polar is harder, at least for the angle. For r, it's easy. Use the Pythagorean theorem and get r is square root of x squared plus y squared. But for theta, it's harder because it depends on where P is in the plane. Is it in the first, second, third, or fourth quadrant? It is going to be true, no matter what theta is, that tangent of theta is y over x, opposite over adjacent. As long as x is not 0, we don't want to divide by 0. That will always be true when x is not 0. But if you try to use the inverse tangent function to solve for theta, there's a problem. It'll give you the right answer if you're over here in the first or fourth quadrant where x is positive, but it'll give you the wrong answer if P is over here in the second and third quadrant, because the output of the inverse tangent function is always over here. It's between negative pi over 2 radians and positive pi over 2 radians. So if you know from the picture that x is negative, or if you're told x is negative, draw a picture. When you take the inverse tangent of y over x, you have to add pi to it to get the right angle, or subtract pi. I mean, these angles are not unique, right? You can add multiples of 2 pi to them as well. What if x is 0? If x is 0, then you're on the y-axis. That's where x is 0. Just look at the picture. If y is positive, if you're up here, then the angle is 90 degrees, pi over 2 radians. If y is negative, you're down here, then the angle can be taken to be negative pi over 2 radians. If you're at the origin, then really the angle is undefined. There's no angle for the point at the origin, though you could take the r to be 0. From this, we made polar graphs of polar functions, r equals f of theta. By the way, it's only the fact that we're using the letters r and theta that makes us think, oh, this should be a polar graph. We could certainly make a regular graph of this thing and label the ordinary axes, horizontal and vertical, with different letters, theta and r instead of x and y. You could certainly do that. But because we're using these letters, it's suggested that we're trying to make a polar graph. As theta varies, you get different distances from the origin. It traces out a polar graph, which is this curve right here. Will I have you make a polar graph on the test? Probably not, right? That's not really the point of a Calculus 2 class. Though maybe I'd give you a graph, and maybe I'd ask you to confirm one point on the graph by plugging in an angle into this formula and figuring out r and seeing, oh yeah, it seemed right. You can label it in the picture. That might be a possibility. But drawing the graph from scratch is not really calculus. What is calculus is to find things like slope, arc length, and area. How do you find the slope? It's not f prime of theta. That's a mistake to think it's f prime of theta, because this graph is made in a different way. It's not an ordinary kind of graph. So how do we figure out what the slope is? We change this polar equation to a set of parametric equations, effectively using these conversion equations up here and replacing r with f of theta. X is f of theta cos theta. Y is f of theta sine theta, giving us a system of parametric equations in the parameter theta, not t, not time, it's an angle. But it traces out the polar curve. It still gives you the exact same polar curve. And then we can use the ideas from way back in chapter 4 about slopes of parametric equations, their curves, to figure out the slope of this. The slope, writing it as dy dx, is a ratio of derivatives of these things with respect to theta. It's dy d theta divided by dx d theta. Now you can look at this kind of equation and sort of imagine informally proving it by canceling the d thetas. That's not really a proof, because those are not literally fractions. You can't literally cancel the d thetas, but you can kind of pretend to. It's a convenient fiction. Really, this comes from the chain rule. I'm not going into details. But then, how do you compute those things? You have to use these equations. And think about this with me here. Look at the right-hand sides. They're products. You need the product rule from Calc 1. Left d right plus right d left. Think about it with dy d theta here first. That's the top. Left d right. F of theta d right means the derivative of sine is cosine. That's left d right plus right sine theta. D left is the derivative of the function. For the bottom of this fraction, dx d theta, left d right becomes negative f of theta sine theta, because the derivative of cosine is negative sine. And then plus f prime of theta cos theta. So that expression, if you know the angle theta, gives you the slope. It's much more complicated than saying it's f prime of theta. So you either have to know what theta is before you find the slope, or you have to figure out what theta is. If you know x and y, you got to use this kind of thing, use the inverse tangent, but then look at the picture, add pi to it if it's over in the third or fourth quadrant to figure out what theta is. You'd have to use this first. So it's a complicated process. Arc length was the next thing. Arc length for parametric curves was the integral of the speed. It was the same as distance traveled. That is the same thing you can do here with these parametric equations. You could write this as the integral of the speed, thinking of the speed as dx d theta squared, well, square root of dx d theta squared plus dy d theta squared. Is it really a speed? Only if theta is the same as time. Now, obviously, it's a different letter. Theta is not t, but maybe the angle is changing with time at 1 radian per second. That could happen. And so if that did happen, you could think of it as time, and you could think of this as a speed. What's the interval of integration? It's going to be the interval that theta varies over. In this picture back up here, maybe theta varies between this angle right there and this angle right there. Use Greek letters, right? That's traditional for angles. Call that one alpha, call that one beta. The Greek versions of A and B. Theta would vary from alpha to beta in general, though oftentimes it's like, 0 to pi or 0 to 2 pi or something like that. It's an arc length integral involving a square root. It can often be difficult to evaluate. If I was going to give you a problem like this in the test and you had to do the integral, I'd have to make the problem so that you could evaluate it. However, when you have f of theta, there's a more common way to write this integral in terms of f. No f's there. I'm imagining I've written x and y in terms of theta, and I'm differentiating using effectively these equations, so f is involved. But in terms of f, it involves these expressions. We saw in class that day before spring break that you can simplify this. You can square these things and add the results and use the fact that cos squared theta plus sine squared theta equals 1 to simplify it a lot. In terms of f of theta, it becomes the square root of f of theta squared plus f prime of theta squared. A little hard to see my prime there. There's a prime in there. Again, not that it's necessarily an easier integral. It could still be difficult. But at least you have the f of thetas in there. And you don't have to use these expressions. So it's simpler that way. And we also found area. Not area under a graph, but area swept out. In this picture back up here, it's not the area under this graph above the x-axis. No. It's the area of the entire wedge. The area swept out by the polar curve as the angle varies. That's what this formula gives you. The formula, fortunately, is fairly simple and usually easy to do, relatively speaking. Integrate, no square roots, but instead 1/2 f of theta squared as theta varies from alpha to beta. We derived these things using, and other things in chapter 8, using Riemann sums and also the infinitesimal approach. Do you have to know that? I might ask you to show a Riemann sum or an infinitesimal, maybe not for a problem like this, maybe more for a problem like about work done by a force, for example. Might be more likely to do it for that kind of thing. If you're interested, I'll just remind you, it's related to the fact that the area of a sector of a circle, piece of pie, where the radius is constant and not dependent on theta, there is an angle in there, theta. The area of that is 1/2 r squared theta when theta is in radians. which should make sense because if you imagine theta to be 2 pi going all the way around and making a full circle, the 2's would cancel and you'd have pi r squared, the area of a circle. Wow, all that was just the very first section. On to the second section. 8.4 was about density, mass, and center of mass in different situations. The simplest situation was when you have a thin rod, right? Effectively a one-dimensional object, maybe a wire would be a better model, or a piece of hair. I think by the way, I think your hair does vary in thickness slightly. And so you could say if you model it as a one-dimensional object, that could be a good example where the density is higher on one end than on the other end. I think that's true. Don't quote me on it as guaranteed. I think it might be true that your hair is not a constant density. But we imagine thin rods that we, for sake of convenience, put along an axis with a left endpoint at some number A, often taken to be 0, and a right endpoint at some number B. And what are we interested in knowing about this thin rod? We're interested in knowing its mass and its center of mass. We're given, for the purposes of doing math, a density function, delta of x, in units of mass per unit of length. You know, usually density is thought of as mass per unit volume, but since we're treating this as a one-dimensional object, it's simpler to think of it as mass per unit length, like grams per centimeter, for example. That's always the units that I end up picking just because it just seems simple and natural because I'm imagining a thin rod. But it could be kilograms per meter, or you could even do a weight density perhaps. But let's keep it at mass density. You know, often's got some formula. You might wonder how realistic is that? You know, that's debatable. But the idea still works, whether you can find a formula for delta of x or not. Let's think intuitively in terms of infinitesimals here. You're at some location x. You should be able to think in terms of either Riemann sums or infinitesimals here, as well as with work done by a force. You chop this thin rod into a bunch of tiny pieces of a tiny width. We could call it delta x if we wanted to use Riemann sums, or we could call it dx if we wanted to think in terms of infinitesimals. Imagining this to be microscopically small, you'd have to see it with a microscope. You have to look at it with a microscope to be able to see it. Effectively, the small mass of that tiny chunk, dm, is delta of x times dx. The units are grams per centimeter here and centimeters here, giving you a quantity in grams because the centimeters would cancel. G is grams here, not acceleration due to gravity. So this would be a small mass in grams, and then to find the total mass, you'd add those up, and you think of the integral conceptually as adding. To find the total mass, add up the tiny masses. But then to actually do the integral, you need limits of integration. And you also need to replace dm with delta of x dx. These two equal signs are not literal equal signs, right, in a real precise way. Though you could say the final equality between this and this is an exact equality. It's kind of funny, two fictitious equal signs merged to give you an actually equal. It's just a fun way of thinking about it, okay? That can be helpful. It's, you know, just don't take it too seriously. It's not rigorous math. It gives you intuition is the idea. And then what else? So that's the mass. If we're going to find the center of mass, we need the moment, right? Capital M. Moment about the origin officially is the name. Found by adding up little moments about the origin. Ultimately doing a definite integral. What are the little moments? They are x delta of x dx. This could be thought of as dm. So effectively for a tiny little chunk that you cut out, dm is its mass and x is its position. That product, x dm, would be the moment of that tiny little chunk. And you're adding those up. But again, you find dm as delta of x dx, and you actually do need limits of integration if you're going to get an answer. Where does the moment idea come from? Comes from the law of the lever, teeter-totters. And generalizing that, I'm not going to go into details. You had some problems involving a finite number of masses. I'm not going to test you on that, but you should be able to use this formula. And then combining these two things, you get the center of mass, call it x bar. It's capital M divided by little m. Which also has applications, which I'll remind you of in a little bit here, from probability. In probability, if delta of x is a PDF, a probability density function, when you integrate it, you got to get 1. The total mass is 1. Little m is 1, and capital M does end up being the mean, which in probability we call mu instead of x bar. Greek letter mu. But it really is the same kind of idea, just applied to a different situation. We did do some problems also where we had thin plates instead of thin rods, effectively two-dimensional objects instead of a one-dimensional object. The example we did in class was a semicircle. And say we've situated this so that the y-axis goes through the middle of it, straight up and down, and the x-axis is along the diameter. And we also have a density function, once again, that could depend on x or it could depend on y, or it could depend on both x and y. And I talked about that one day. I mentioned it's multivariable calculus and you do a double integral to find these things, but that's multivariable calculus. You're not going to be tested on it, at least that kind of problem. So we would want to restrict ourselves to a situation where this depends on either x or y. If it depended on x, you would want to slice this with thin vertical slices because that's at an approximately constant value of x. The width of the slice, okay, let's go ahead and call it dx. I'm treating things as infinitesimals mostly here at the moment. And the height, I mean, you could call it h of x for a height. I think in class that day I called it L for length. It would depend on x in this situation as well. If, on the other hand, your density function depended on y instead of x, then you'd want to use thin horizontal slices at approximately constant values of y. This density would be in mass per unit area, not mass per unit length. The area of this thin slice, the thin slice, by the way, is right there. dA would be L of x dx. Combine these things, the total mass would effectively be adding up the densities times the areas. Delta of x dA. As an idea, a conceptual equation. But how do you actually compute it? Like, you know, what is A? It's not a variable in this picture. It's representing an area. You got to relate it to x. dA is L of x dx. So go ahead and make that replacement. this is the integral you'd have to do from A to B. In this case, say negative A to positive A. That would be the mass. In general, it might be from some value x equals A to some value x equals B. And the moment, capital M, would be the same integral except also multiplied by x before you integrate. I won't go through the derivation. The reason we need this extra L of x function in here is because for one thing, this length, this height depends on x. And for another thing, this density function is in grams per unit area, not grams per unit length. Now, once again, x bar, x coordinate of the center of mass is capital M divided by little m. If this density were constant, by the way, if this were a constant, which I think we did an example of that, the capital M integral would be 0. This L of x function would be an even function. It's this graph. X times that would be an odd function times a constant. Integrating an odd function over such an interval would give you 0, as would make sense. If it's a constant density, x bar should be 0. The center of mass should be on the y-axis by symmetry. We also did problems, I'm not going to go into detail for sake of time, about population and mass of the atmosphere. Do you remember doing that? We had a city shaped like a circle, just for the sake of doing it. Not that there are many cities shaped like circles. And the density, the area density, depended on the distance from the center of the circle. Call it R. Delta of R was the density in, say, 1,000 people per square mile or something like that. 1,000 people per square mile is what that says. 1,000 people per square mile. And you'd have to slice the circle, not with vertical or horizontal slices, but with thin ring slices at approximately constant values of R. That's why you do it that way. Multiply the density times the small area, which would involve imagining cutting that thin ring and unrolling it so it looks almost like a rectangle of small width dr and base equal to really the circumference of the circle, 2 pi r. Add those up to get the total population. Do an integral. Should be 2 pi r delta of r is the function you integrate. You could also apply this idea, for example, I think this comes up in some problems in the book, like if you got an oil slick that's, it's expanded and now it's not expanding anymore. And the density of the oil slick depends on R. You could figure out the mass of the oil. There's also the mass of the atmosphere. We talked about that in class. By imagining the atmosphere as being made up of thin spherical slices instead of circular slices, that's probably a bit too far to put that on the test. But we did do it. You can look it up in your notes. Bit too much to handle. The next section was about work done by a force, more physics, and also problems related to pressure and force. Water pressure in particular. So I don't have time to go into details, but just to remind you, in the simplest case, the work done by a force is just the force times the distance traveled if the force is in the same direction as the distance traveled. You could think of those things in terms of vectors if you like. Maybe this is F here and this is D there. The key thing is they got to be in the same direction if you're going to use this equation. More importantly for calculus, though, was to apply this to a couple different typical kinds of problems. One of which involved like hauling an anchor or a weight up out of the water or up the side of a building using a rope or a chain, something like this, some kind of picture like that. And you wanted to figure out the work done to do this. The anchor or the box, whatever it is, has a constant mass in kilograms or weight in pounds. And to calculate the work done on that, you just do this product. The force, which is a weight, times the distance it goes. If you're using British units, the non-standard, non-scientific units, pounds, that's already a force. It's actually easier. But if you're using standard SI units, then mass in kilograms is not a force. You got to multiply by 9.8 to get the force, the weight. In newtons, technically speaking. As far as the calculus goes, it's related to the rope or the chain. And the fact that different little chunks travel different distances. A given little chunk of, say, length dy travels distance y. Use that idea to come up with an integral for the work. If I give you a problem like this, I will make it simpler, and you'll pull the box all the way to the top of the building. And that means the entire bit of rope goes to the top of the building too, make it a little easier. We also had work problems involving pumping water out of a pool. The pool could be like cylindrical or maybe rectangular box shape, or it could be a cone, or the typical kinds of examples. And the way we figured out the work done there to pump all the water out of the pool, it was kind of funny. You might say phony. We imagine slicing the water into thin slices. And in your imagination, even though this is not literally what happens, imagine the entire thin slice of water going upwards against gravity as you pump it out. The weight of that, the force in newtons or in pounds, is constant. But the distance it travels is variable. And it also, the volume could be variable if it were a cone as well. And that's why you end up needing an integral. We ignored practical thoughts like, what's really happening? Aren't those water molecules going all over the place? And if the hose is down at the bottom of the pool, don't they go down first before they go up? You ignore all that. Evidently, it still works. I was wondering about that. Like, why does that work? I went to a physicist and asked them, why does it work? He's like, I don't know, just do it. You could sort of pseudo justify it maybe by saying when the molecules go downward before they go up, maybe that's like a negative work done. And then more work done as it goes up all the way, and it cancels out to give you the right answer. Don't worry about practical thoughts like that. I mean, yeah, maybe you should really worry about it if you're truly an engineer, but I mean, people have done experiments with this stuff, I imagine, and evidently it comes out right, or approximately right. Work does have units of joules, so it is directly related to the amount of energy required to pump the water out of the pool. Other problems included force, pressure, water pressure and force. From water pressure. Simplest, no calculus necessary if you, for example, have an area that's maybe a thin plate sitting horizontally underwater at a constant depth. Right? Because then you just take the volume to figure out the pressure. Let's see, pressure is force per unit area. 62.4 pounds per cubic foot. That's the weight density of water. You have to know that for the test. No, I'll give it to you if you need it. Cubic foot of water weighs 62.4 pounds, about so big, weighs 62.4 pounds. And you multiply that by the depth to get the pressure. And then for the total force on the horizontal plate, you'd have to multiply by the, divide by the area. No, multiply by the area. Pressures in pounds per square foot, multiply by the area in square feet to get the pounds, the force on thin plate. If it's SI units, the mass density of water is 1,000 kilograms per cubic meter, about yay big. Has a mass of 1,000 kilograms. And you have to multiply that by 9.8 as well before multiplying by the depth. More interesting for the sake of calculus is if you've got a dam like the Three Gorges Dam shaped like a rectangle, or maybe one shaped like this, and you want to figure out the total force due to water pressure along the side of the dam, you got to break it up into thin slices at approximately constant depth. Figure out the total force on that thin slice, add up those forces to get the total force by integration. Not going into details, you do need to take the time to practice these things. There are a lot of ideas here. It's going to require some practice. From there, we went on to financial applications. And I'll combine that with probability. Actually, I hope you remember, we've actually been doing probability since the beginning of the semester. Along about the second week, I think I did talk about applications using normal curves. Integration, applications to integration, or of integration. Then we got here in chapter 8, more challenging, involving random variables and lifetimes, and using the transformations to figure out present values of future payments for the applications for actuaries, to warranties, or to life insurance. The basic equations, you got your compound interest. For future value, call it B, and present value, call it P. If you're using the standard formula, where you've got n compounding periods per year, it looks like this and like this. You just switch to go from future value to present value. You switch around the P and the B. And you also change the exponent from positive NT to negative NT. But for continuous interest rate, which we like because the formulas end up involving E, they look like this. We, of course, like that in calculus because that kind of exponential function is easier to deal with calculus-wise than this kind is. Right? Easier to differentiate and integrate. And what we're doing in this particular section was integrating them. No calculus really there because it's just algebra formulas. You could teach this in a pre-calculus class, and maybe you even learned it in pre-calc. The calculus comes into play with cash flows, for example. You got a cash flow, F of t, which in general doesn't have to be something simple. It could be something crazy. Think about Amazon, for example. They got cash flow, money come into their system every second of every day from all around the world, sometimes faster than others, right? During Christmas season, it's coming in faster than during January. So the cash flow is not constant. It's a function of t. That's kind of complicated. We have enough trouble understanding what's going on. So we take it to be simple. We take it to be a constant cash flow. And maybe this is in dollars per year. Maybe for fun, we imagine Elon Musk is paying us money at a rate of 10 to the ninth million dollars per year. $1 billion per year. Coming in at a constant rate every second of every day. That doesn't mean you get $1 billion every second of every day. It means you get $1 billion over the whole year. By the way, just for fun, how many seconds are in a year? 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and on average, 365 and a quarter days per year. On average, there's 31,557,600 seconds in a year, including leap years. So if you're getting $1 billion over the course of a year at a constant rate, there's $1 billion. How many dollars are you getting every second of every day? $31.69 every second of every day for a year, or maybe even better, over 10 years. Giving you $10 billion total over that time period. What's its present value? What is it worth right now? You have to integrate to find that present value, because different tiny chunks of money are coming in at different times. At a given time t over a small interval of time dt, the amount of money, should I call it dm? M does not mean mass here, it means money. Maybe I should call it dA for amount or something, but that would be confusing too, because then you think it's an area. dm, the small amount of money there over that small amount of time, would be f of t dt. Dollars per year is f of t. Number of years is dt. Giving you units of dollars here. And then the total amount of money would be the integral of that, but that's not quite what we're interested in. We're interested instead in the present value of that. The tiny present value of that tiny amount of money would be found by using that formula there, assuming we've got a continuous interest rate. The B would be the amount of money there. That would be the f of t dt. And then I have to multiply by e to the negative rt. It's a little weird putting the dt between those things. So more typically, we'd put it on the right. We'd write this as f of t e to the negative rt dt. Or maybe switch around the order of those. It's not a big deal. And that means the total present value of the entire cash flow would be the sum of those tiny present values, which would be the integral of f of t e to the negative rt over the entire time interval. I went from 0 to 10 here. Though I could have picked something else. So that integral gives you the present value of the entire cash flow at interest rate R. The answer does depend on what R is. It depends on what the going interest rate for investments is right now. That's how you assess what you should do with the money right now, or what you should pay for this income stream if you're going to pay for it, which you would often do sometimes. Well, not everybody does it, but many people do at retirement. Take a breath. What about probability and random variables and all that stuff? Probability. We are talking about continuous models. Of course, there's discrete probability too, like flipping a coin, right? Could come up heads, could come up tails. Technically, somebody could open that door as I flip a coin, and a dog could come running in the room and jump and eat the coin. Or a gorilla could run across the back of the room. You saw me in the Clarion saying that. That did happen in a classroom once. A gorilla ran across the back of the room. Yeah, it was somebody in a gorilla costume. But it happened. That's discrete probability. No calculus, really. We don't want to apply this to calculus, so we need continuous probability. In general, you've got a random variable x. A continuous random variable It's just a symbol that we use a capital letter with because we want to use some lowercase letters as well, just representing a quantity whose value we don't know, and it takes on values by chance. Like what? Oh, like the random height of a random person, right? I look, there's no more phone books these days. Back in the 80s and even in the 90s, we used to have phone books. Everybody's phone numbers in the phone book. Unless you said, I don't want to be in the phone book. Now, randomly pick a page, close your eyes, randomly put your finger down in the phone book. You found somebody. Go to their house and say, can I measure your height? Assuming they let you, you get a height. You have observed a value of the random variable representing a random height of a randomly chosen person. What are the chances that it's between 5 feet tall and 7 feet tall? Probably 0.999 or something. Well, maybe not that extreme. 0.99. You have assessed the chances ahead of time through some model. That's what it's all about, okay? What is the model? The model is the probability density function, PDF. Little f of x. It's very similar to the idea of a mass density for a thin rod. Except the units are not mass per unit length, but probability per unit length. That's kind of weird to think about, but true. Does probability have units? Maybe if you say it's the word probability, that's the units. Chance, okay? It's some function that could be defined for all x like a normal curve, though most of the examples we did were not that way. Maybe here's a general one, maybe like this. I think we had one example like this. Where the density function is higher, the probability accumulates at a faster rate, you might say. If you had data that this was a model for, the data would be denser where the PDF is higher and less dense where it's lower. If you use the function, like with Mathematica, to do simulations, we saw with the simulations that the simulated data is more dense where the PDF is higher. These things are models. You choose f of x so that the probability that capital X takes on a value between a and b is the integral of little f. Now realize all of applied math is about approximations. Is this exactly right in a given situation? Probably not, right? It's all approximations. You hope it's a good model. You hope to choose little f, so this is approximately right. Once you got the PDF, you can also find the CDF, cumulative distribution function, capital F of x, which is always the probability that the random variable is less than or equal to the given quantity. Notice the capital X versus the lowercase x. For continuous random variables, you can find that by integrating the PDF from -infinity to x. Use a different letter like U here for the variable of integration. Being that the upper limit is x, the FTC part 2 from chapter 6 would imply that the derivative of capital F is little f at any value of x. In other words, capital F is an antiderivative of little f. And therefore, you can use it to find probabilities to do these integrals as capital F of b minus capital F of a by FTC part 1 from chapter 5. Where the graph of capital F is highest in slope is where probabilities are accumulating fastest. Because the derivative of capital F is little f. Little f is telling you the slope of capital F. If it's highest there, that's where the graph of capital F is going to be steepest. And these are both useful functions. The PDF is useful for finding the mean, the average, denoted with a mu. There's mu. I love that letter. Looks like an M, looks like a U. It's called a mu. Isn't that great? Theoretically, it's an integral over all x of x times the PDF. Again, I'm writing these things as improper integrals, but they don't have to be improper integrals. In the applications we looked at with warranties of lifetimes of refrigerators, for example, or income streams for a person who retires until they die, you could start the integral at 0 because the PDF was 0 when the variable was negative. And maybe you don't have to go up to infinity either, because maybe there's a, like a kill switch for a refrigerator. It's not going to last past 20 years and the PDF is 0 afterwards as well. The median is another measure of center. It's where the CDF takes on a value of 0.5. So X sub med equals 0.5 is the condition to be the median. To find it, you'd have to solve that equation. Here you'd have to do an integral. Here you'd have to solve an algebra equation. But then we applied this, of course, to these warranty problems and these lifetimes. To, for example, model present value random variables. Z was the name we gave to the present value of a one-time future payment, like a warranty payment when your refrigerator dies. It's a little confusing because in stats, Z also means standard normal. So we're going with what actuaries use here. $1,000 payment, say, at time capital T. If you multiply 1,000 by e to the negative r times capital T, that gives you the present value, where r is the continuous interest rate. In our examples, we did 5%, I think. Homework, you had 4%, or maybe it was vice versa. And our goal was to find information about Z, first by finding its CDF. It was called the CDF method. And just a real quick calculation here. You have to solve this inequality for capital T. And in the end, what you end up getting is, using the fact that probabilities have to add to 1, the inequality changes direction once. You end up having to get 1 minus the probability that capital T is less than or equal to, what would it be here? I think it was going to be negative 1 over r ln of Z over 1,000, it looks like. Just doing some algebra in my head there. Divide both sides by 1,000, then take the log, then divide both sides by negative r. And then you'd have the inequality be the other direction. So to get it to be this direction, you have to subtract it from 1, because probabilities have to add to 1. This is then capital F of negative 1 over r ln of Z over 1,000, where capital F is the CDF for capital T, the lifetime. We did examples where the PDF was like a horizontal line or a triangle, and you had to figure out the CDF from those. Once you've got that, you can find the PDF, little g, by differentiation. Then you can find your mean and median, and those are useful things. We also did this kind of stuff for what I called capital Y, which was the present value of an income stream. Like when you retire, you buy an annuity, it pays you money until you die, but the time you die is unknown. So the upper limit of the integral is unknown, capital T. It would be a present value integral, something like this, for some value of r. And then you had to simplify that and do the same kind of things we did here. Find the CDF and the PDF and the mean and the median. Well, you have to do a full one of these on the test. Not completely from scratch, but a partial. It just takes too long doing it completely from scratch. Then, of course, now in 11 minutes left in class today, chapters 9 and 10. Whoa. Okay, so I went slower over chapter 8 there. I have to go faster here over chapters 9 and 10. It might have seemed like we were going fast enough as it was, but right? Sequences, first of all, in chapter 9. Intuitively, as an example, a sequence is just an infinite list of numbers that may or may not have a limit as you keep going to the right. If that list has a direct formula like this one does, 1 over n, you can often pretty easily see what the limit is. This clearly approaches 0 as n goes to infinity. It never equals 0, right? But it gets arbitrarily close. I can make these numbers as close as I like to 0 by making the n big enough, is what this means. There are also examples with indirect formulas. For example, maybe Sn is Sn minus 1 squared. Though if you do that, you do need a starting value, and S1, maybe 0.5. That would be an indirect or recursive formula. You should be able to use your calculator to find values after 0.5. You take the preceding value and you square it. And then you can just keep squaring. So if S1 is 0.5, S2 would be 0.5 squared, which is 0.25. S3 would be 0.25 squared, which is 0.0625. Then S4 is this. S5 is this. These numbers get small pretty rapidly. S6, S7, S8. By the time we reach S9, no, S10, we're past lower than 10 to the negative 100 power with this example. And the calculator could say underflow, but decides to round it to 0. It doesn't actually equal 0 ever, but it gets arbitrarily close very rapidly. This one goes to 0 as well. You could use this kind of notation. You could also use limit notation. The sequence converges to 0. Most important for us, though, in Calculus 2 is using sequences to define what series are. Here's a general series, which you should be comfortable writing in summation notation or not. But don't forget your plus dot dot dots if you write it out this way. I keep emphasizing that. It's an infinite sum. Wait, really? Are we really adding up infinitely many numbers? No, we're just pretending to. But we're pretending to in a way we can make rigorous and in a way that's useful, amazingly. As I always emphasize, calculus really is full of convenient fictions. And that's serious. You can make them rigorous, though. And they are useful, amazingly. How do I make this rigorous? This is really key, and lots of people have trouble with this. You have to relate it to sequences and what it means for sequences to converge. When you're talking about an infinite series like this, you create the sequence of partial sums, which represents finite sums, not infinite sums. Sn is the sum of the first n terms. A finite sum, no problem making sense out of that. We know what it means to add up finitely many things. I mean, the finite number of things could be humongous, like a Google things, but in theory, not that you would want to do it in practice, but in theory, you could think about doing it. The convergence or divergence of the series is completely dependent on the convergence or divergence of this sequence of partial sums. That's how it's defined. If Sn converges to some number S, as n goes to infinity, then we say the series, the infinite sum, so to speak, converges to the exact same thing. Then the infinite sum also converges to S. I could write those words, but for shorthand, we say it equals S, as if we have added up infinitely many things. But no, we're only pretending to. But we're making it rigorous, we're making it precise by relating it to this sequence of partial sums, and then relating it ultimately to what it means for them to have limits. Sn approaches S means you can make Sn as close as you like to S by making n sufficiently large. Problem with series, though, unlike improper integrals, is it's hard in general to figure out whether they converge or not. We need a bunch of different tests. Of course, geometric series are nice because we have formulas. If I've got a finite geometric series with n terms, where the first term is a times r to the 0 power, the answer is a times 1 minus r to the n over 1 minus r, as long as r is not equal to 1. If it's an infinite geometric series, going on forever without stopping, then it converges to a over 1 minus r if the absolute value of r is less than 1. How do you get from here to there? You let n go to infinity. If the absolute value of r is less than 1, then this thing goes to 0. So geometric series are, well, they're useful in many contexts, and they're just nice because they got nice formulas. But there's plenty of series that don't have nice formulas. The most prominent one that's still somewhat basic looking is P series. And you should know, ideally for the rest of your life, this converges if P is bigger than 1 and diverges if P is less than or equal to 1. How did we prove that? We used the integral test. By the integral test, where we use knowledge about this improper integral to help us decide. This improper integral also converges when P is bigger than 1 and diverges when P is less than or equal to 1. The improper integral is easier to handle because we have the fundamental theorem of calculus to find the antiderivative and use that to find the integral. These things are hard to handle because there's no simple formula for their partial sums. There's no analog of the fundamental theorem of calculus. But the convergence is completely related to the convergence of this. The value, though, is hard. And, when P is 2, it took an Euler's genius to figure this out to be pi squared over 6. When P is another even power, then it's a fractional multiple of pi to that same power. P is odd, then it's, you're getting into difficulty there with the Riemann zeta function and the Riemann hypothesis. That coming up next Wednesday, when I also talk about complex numbers. There'll be a lot of interesting things there. For the moment, you just got to know this. You can use it then also for comparison test. I'm just going to quickly write down the different tests. Comp test means comparison test. In the book, there's also the limit comparison test. We skip that. I think in the extra video I'll share, I might do a limit comparison test problem on that video, but you don't need to use it on your test. We also had the ratio test related to looking at what do these ratios approach as k goes to infinity. If it's something less than 1, then the series converged. If it was greater than 1, then the series diverged. And if it equaled 1, the test gives you no information. The ratio test always actually gives you no information for P series, actually. The integral test is more powerful. But the ratio test is still useful, as well as the alternating series test. And error bound for that. And these things are useful for power series in figuring out the interval of convergence and the radius of convergence. And finally, our last topic, the first 3 sections of chapter 10, were Taylor polynomials and series, where you've got a function f of x that you'd like to expand as a series, a power series, a special kind of power series, using its derivatives. And you should know the formula involving the derivatives, or using a trick, like we did a bunch of tricks on Monday. Okay? And in particular, you should make sure on your note card that you have the series for 1 over 1 minus x, for e to the x, for cos x, for sine x, maybe even for ln of 1 plus x and arctangent of x. We derived all those. Probably not for something like this. We did this example on Monday, but we did not, it's not something you should write on your note card. We've used the series for these two, substituted negative 2x for e to the x for the e to the x series and 3x for the cosine series, and then multiplied the series. We also did the tangent one by a long division. Well, I make you do a long division of series, and I'm not completely ruling it out, but I don't think I typically do. I'm not ruling it out at the moment. I still need to write your exam, by the way, this afternoon. Okay. So in reviewing all this stuff, I'm reviewing for the exam as well. So I spent a lot less time on the recent stuff because it's recent stuff. It's in your memory better. A lot longer on the chapter 8 stuff. Okay. Because you may have forgotten a lot of it.